Let's now consider the solutions of weak electrolytes, that is, weak acids and weak bases. Now, before we begin over it, we must consider certain conditions. We need to understand that all these calculations that we are doing, all these derivations that we are doing, are for the solutions of nearly 0.1 molar concentrations. Any concentration much lower than this, the contribution from water will become effective and the calculated values will be different from the observed values. In all these calculations, contribution from water has been neglected. A very dilute solution, we won't be able to neglect it. We start with the discussion with a weak acid, maybe acetic acid. When acetic acid is put in water, an equilibrium will be established. Acetic acid aqueous will interact with liquid water to give hydronium ion aqueous and acetate ion aqueous. Here again, water is present in a huge excess and is the solvent as well. So the equation is written excluding water in the form of acetic acid aqueous in equilibrium with H plus aqueous and acetate ion aqueous. Here again, we have made the equation in a form where we have only one reactant on the left hand side. So here again, we use the degree of dissociation. 1 mole of acetic acid, if completely dissociated, would give 1 mole of H plus and 1 mole of acetate ion. Now, if we consider that alpha moles of acetic acid is being dissociated, then it is going to give us alpha moles of H plus and alpha moles of acetate ion. Multiplying the entire equation by the concentration of acetic acid, that is C, we get C1 minus alpha gives us C alpha of H plus ion and C alpha of CH3COH ions. Multiplying the entire equation by concentration of acetic acid, that is C, we get the final concentration of acetic acid as C1 minus alpha. C alpha of acetic acid is being dissociated. It gives us C alpha moles of H plus and C alpha moles of acetate ion. The equilibrium constant of this reaction would be Ka. Here we have put the subscript A for the dissociation constant of an acid. That's equal to the concentration of H plus and acetate ion divided by the concentration of acetic acid. That would turn out to be C alpha multiplied by C alpha divided by C1 minus alpha. C and C cancel out. We get C alpha square divided by 1 minus alpha. Again, acetic acid is a weak electrolyte. The dissociation is much smaller, that is, alpha is much smaller to 1. Hence, in comparison to 1, alpha is not required. So 1 minus alpha in the denominator simply becomes equal to 1. So here, Ka becomes equal to C alpha square. The degree of dissociation can be represented in terms of dissociation constant and concentration. Alpha is simply equal to the dissociation constant divided by concentration and whole taken the square root of. The equation suggests the concentration of H plus is concentration multiplied by degree of dissociation, that is C alpha. So this would turn out to be the square root of the product of the dissociation constant multiplied by the concentration of acetic acid. Since we have the concentration of H plus, we can easily find the pH. Taking the log of the equation we have, we get log of the concentration of H plus is equal to 1 by 2 log of Ka plus log of concentration. Multiplying the entire equation by minus 1, we get the negative log of H plus is equal to 1 by 2 negative log of Ka plus negative log of concentration. For any number, the value of which could be more than 1, we do not use the symbol P for the negative log. Since concentration is not necessarily less than 1, we do not use the convention of P for the negative log of concentration. Hence, the equation becomes pH is equal to 1 by 2 pKa minus log C. Calculate the pH and dissociation constant of 0.1 molar acetic acid at 298 Kelvin if it is 1% dissociated. In this question, the concentration is 0.1 and degree of dissociation alpha is 1%, that is 0.01 or simply 10 raised to power minus 2. Ka is concentration of H plus into acetate ion divided by the concentration of acetic acid, that is equal to C alpha square, and that's equal to 0.1 into 0.01 square. So that turns out to be 10 raised to power minus 5. pH is 1 by 2 pK minus log C. That is equal to 1 by 2 of 5 plus 1, and that's equal to 3. In the same manner, we can work for the dissociation of a weak base, that is ammonium hydroxide. We add ammonia to water. Ammonia interacts with water to give ammonium ion and hydroxide ion. We may consider the association of ammonia with water as ammonium hydroxide. Now, considering ammonium hydroxide, it will turn out to be in equilibrium with ammonium ion and hydroxide ion. 1 mole of ammonium hydroxide would give 1 mole of ammonium ion and 1 mole of hydroxide ion. If we consider it to be undergoing dissociation and the degree of dissociation to be alpha, then alpha moles of ammonium hydroxide would give alpha moles of ammonium and alpha moles of hydroxide ion. Multiplying the entire equation by concentration of ammonium hydroxide, we get the final concentration of ammonium hydroxide as C1 minus alpha. The amount of ammonium hydroxide undergoing dissociation is C alpha. C alpha moles of ammonium hydroxide would give C alpha moles of ammonium ion and C alpha moles of hydroxide ion. The equilibrium constant for this reaction would be termed as Kb, B signifying the base. So Kb is equal to ammonium ion concentration multiplied by hydroxide ion concentration whole divided by ammonium hydroxide concentration, which could even be considered the ammonia concentration. That is equal to C alpha multiplied by C alpha divided by C1 minus alpha. That is equal to C alpha square divided by 1 minus alpha. Again, alpha is insignificant in comparison to 1. So we can simply neglect alpha in comparison to 1 in the denominator, and we get Kb is equal to C alpha square. The value of alpha would now turn out to be the square root of the dissociation constant of the base Kb divided by the concentration of the base. In this case, we have the concentration of hydroxide. The concentration of hydroxide would be equal to the concentration of the base multiplied by the degree of dissociation, that is, it becomes C alpha. Now C alpha would be under root of the product of the dissociation constant of the base and concentration, that is simply the square root of Kb into C. Since we have the concentration of hydroxide, we can easily find the POH. Now here, the log OH minus would be equal to 1 by 2 log Kb plus log C. Taking the negative of this equation, we get minus log of OH minus is equal to 1 by 2 minus log Kb plus minus log C. POH is equal to 1 by 2 of Kb minus log C. POH is equal to 1 by 2 pKb minus log C. pH is equal to pKw minus POH. Let's have a question. Calculate the degree of dissociation and concentration of ammonium hydroxide solution if its pH is 11 and dissociation constant Kb is equal to 10 raised to the power minus 5 at 298 Kelvin. Now we know POH is equal to pKw minus pH. Taking the temperature 298 Kelvin, pKw is 14 and pH given in the question is 11. So we get POH as 3. Now we know POH is equal to 1 by 2 pKb minus log C. Substituting the value of POH as 3 and pKb as 5, we get 3 is equal to 1 by 2 of 5 minus log C. This equation gives us the value of C, that is the concentration of ammonia, as 0.1. Now, alpha is equal to under root of Kb by C. That will be equal to under root of 10 raised to the power minus 5 by 0.1. The answer turns out to be 0.01. So the degree of dissociation is 0.01, 10 raised to the power minus 2, or simply 1%. Let's consider a simple question, which would require more volume of 0.1 molar sodium hydroxide for complete neutralization. Will it be 100 milliliter of 0.1 molar hydrochloric acid or 100 milliliter 0.1 molar acetic acid? Maybe you are tempted towards a certain answer. The difference, that is the thing which you would be considering here, is HCl is a strong acid which is completely dissociated, while acetic acid is a weak acid which is partially dissociated. Is it HCl or is it acetic acid? Let me describe an incident to you. Once I was driving from Delhi to Chandigarh. On the way, there were certain people selling guavas. They had a few guavas on a small table along the roadside. I thought that I would take a few for the way. I halted the car near one of them and asked him, "What's the price?" In return, he asked me, "How much do you want?" I was a bit surprised. I could see only a few guavas, and then this person was challenging me as to how much I would buy. Just to show him, I said, "Only 5 kg. He said, "The rate would be rupees 30 per kg. I was still curious, so I said, "Okay, give it." I thought the bluff would be called off now, but I couldn't imagine that the joke was actually on me. He simply asked a young boy sitting along with him to get 5 kg guavas. The boy promptly got up, walked towards a flock of trees, and after a few minutes came back with bags full of guavas. At that time, I realized that this person was sitting near to a guava plantation, and if I asked for a much larger amount also, he would have given it to me easily. The guavas on the table were just the sample, like the one you have in the display window of the showroom. Well, I had to buy 5 kg. Not that I regret it, it was quickly consumed by all the people I met later that day as they were fresh and really nice. Still, it gave me a lesson not to judge the total quantity just by what you see as a sample. The same is the case with a weak acid or a weak base. Only a small amount of it dissociates, hence a very small of it is visible as the pH or the pOH. But it has a large amount of reserve acid or a base equal to its total concentration. This is consumed whenever there is a demand from the added base or the acid. The sample, in fact, is the last to be consumed once the reserve has been exhausted. The pH of the weak acid or the weak base in its neutralization reaction remains almost a constant up to the end of the reaction. Hence, the observation tells us that HCl and acetic acid will consume the same amount of NaOH for the complete neutralization. When we try to react acetic acid with sodium hydroxide, the amount of H plus that has been already dissociated will react with sodium hydroxide. The decrease in concentration of H plus, which is the product in this reaction, will shift the reaction to the forward direction and create more of H plus. This will continue till the time entire acetic acid is consumed. Hence, the amount of OH minus consumed will be equal to the amount of acetic acid that is in the system rather than the amount of H plus that we see as pH. This tells us that the HCl and acetic acid, they both will consume the same amount of sodium hydroxide. Such system which contain reserve acid and base so that they can consume a small amount of added acid or base without any significant change in pH are termed as buffers. These are compounds that resist changes in pH upon the addition of limited amounts of acid or bases. Buffer systems are usually composed of a weak acid or base and its conjugate salt. The components act in such a way that addition of an acid or a base results in formulation of a salt causing only a small change in pH. For maintaining a high pH, a concentrated solution of a strong base is used. To maintain a low pH, a concentrated solution of a strong acid is used. For maintaining a pH near to neutral, the strong acid or strong base will not be effective as there would be a very dilute solution, and that will be quickly consumed the moment we add another acid or a base. In such cases, the concentrated solution of weak acid or weak base are used, along with their salts. The concentration is high, so can consume a significant amount of acid or base, but the dissociation is low, so the pH is near to neutral. Further, a concentrated solution of a weak acid will be able to consume the slight amount of base added to it, and a weak base will keep the pH constant if an acid is added to it. But if an acid is added to a solution of weak acid, it will show a significant change in pH, as weak acid has nothing to consume the increased H+. In the same manner, if we add a strong base to a solution of a weak base, it will not be able to stop the pH change, because the weak base has nothing to consume the OH- added by the strong base. Now, if we add the salt of the weak acid to the weak acid, we have something else. The salt is a strong electrolyte and completely dissociates. The anion formed by the dissociation of the salt is the conjugate base of the weak acid. This conjugate base becomes the reserve base in the mixture. When an acid is added, this conjugate base consumes the pH+ and the pH is maintained. In case of weak base also, its salt is added. This provides its conjugate acid, which becomes the reserve acid and consume the hydroxide ion added. Further, the salt added provides a common ion which reduces the ionization of the weak acid or the base. This gets the pH even nearer to the neutral pH. The mixture of a weak acid or a weak base, along with their respective salt, have reserve acid as well as reserve base, and are able to maintain the pH near to neutral when a small amount of a strong acid or base are added to them. So these solutions are buffers. Buffer capacity. It is a measure of the efficiency of a buffer in resisting changes in pH. Conventionally, the buffer capacity, that is beta, is expressed as the amount of strong acid or base in gram equivalents that must be added to 1 liter of the solution to change its pH by 1 unit. We calculate the buffer capacity as beta is equal to delta B divided by delta pH, where delta B is equal to the gram equivalent of strong acid or base to change the pH of 1 liter of buffer solution, and delta pH is the pH change caused by the addition of strong acid or base. The buffer capacity depends essentially on two factors. One, the ratio of the salt to the acid or base. The buffer capacity is optimal when the ratio is 1:1. That is, the concentration of the salt and the acid are same, or the concentration of the salt or the base are same. When pH is equal to pK or pOH is equal to pKb. The second factor is the total buffer concentration. For example, it will take more acid or base to deplete a 0.5 molar buffer than a 0.05 molar buffer. Let us discuss one acidic and one basic buffer. The first one, acetic acid sodium acetate buffer. Let's have a relook at the dissociation of acetic acid. Acetic acid on dissociation forms acetate ion and hydronium ion. Now we add sodium acetate to it. Being a salt, sodium acetate is a strong electrolyte and is completely dissociated. It has the ion common to the dissociation of the acid and shows common ion effect. The acid is weak and so the dissociation is negligible in comparison to 1. Further, the addition of the salt has made the dissociation even lower. In such situation, the entire amount of acetate ion, that is CH3COO-, may be considered to be from the salt. Since salt is a strong electrolyte, it is the concentration of the salt itself. So Ka can now be considered to be the product of the hydronium ion and the concentration of the salt divided by the concentration of the acid. Taking the log of the equation, we get log Ka is equal to log H plus log of the salt divided by the concentration of the acid. Interchanging the side of the log of hydronium ion and Ka expression, we get the pH. pH is equal to pKa plus log of the concentration of the salt divided by the concentration of the acid. This equation is termed the Henderson-Hasselbalch equation for a weak acid and its salt. Similarly, we can get the equation for the buffer made by mixing a weak base with its salt. Let's take a combination of ammonium hydroxide with ammonium chloride. The base is weak, so the dissociation is negligible in comparison to 1. Further, the addition of the salt has made the dissociation even lower. In such situation, the entire amount of ammonium ion is from the salt. Since the salt is a strong electrolyte, it is the concentration of salt. So the dissociation constant now becomes the product of the concentration of hydroxide and the salt divided by the concentration of the base. Taking the log and interchanging the side of the log of hydroxide and Kb, we get the POH. Subtracting POH from pKw, we get the pH. This is the Henderson-Hasselbalch equation for a weak base and its salt. A question. Calculate the pH of a buffer made by mixing 0.1 moles of sodium acetate with 1 mole of acetic acid in 100 milliliter of the solution. Take the Ka of acetic acid to be 10 raised to the power minus 5. Answer. First of all, since the acid and salt are present in the same volume, the volume cancels out and the ratio is just of the moles of the salt and the acid. Using Henderson-Hasselbalch equation for a weak acid and its salt, we get pH is equal to pKa plus log of the salt concentration divided by the acid concentration. That is equal to 5 plus log of 0.1 divided by 1, and that's equal to 5 minus 1 equal to 4. The pH of this buffer is 4. Another question. Calculate the mass of sodium acetate, CH3COO-Na, having molar mass of 82 grams per mole, that must be added to 6 grams of acetic acid, CH3COH, molar mass 60 grams per mole, to get 500 milliliter buffer solution of pH 6. K again is taken as 10 raised to the power minus 5. Let the mass of salt be X. the pH is equal to again pKa plus log of concentration of salt divided by concentration of acid. That would give us 6 is equal to 5 plus log of x by 82 divided by 6 by 60. Changing the side of 5, we get 1 is equal to log of 10x by 82. Taking the antilog of the equation, we get 10 is equal to 10x by 82. Antilog of 1 is 10. Solving it, we get x as 82 grams.